Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today we're going to be looking at electricity. Let's take a look at this. Electricity. Electricity is such a fascinating thing because our whole world relies upon electricity. And in the next couple or series of videos, we're going to be learning a little bit about how to make electricity do something. Remember, electricity is just electrons moving. So in a circuit, at the most simplest, is we use something like a battery, a 9-volt battery. Notice I've got wires sticking out of them, and they got these little clampy things on them. Well, what I can do is I can hook the clampy things up to what I've got is here a series of light bulbs. Now, ignore the extra wires. I'm just going to put this light bulb or and clamp it on here across this first light bulb. And what happens when I touch? Note. Light bulb goes off. That's light bulb number 1. Now if I want to get light bulb number 2 to go off, if you kind of look at it, I have green going to here, yellow coming to here, and then the electricity is going to pass across here, red to here, and now I'm going to hook up this yellow one down to here. Now what I'm going to do is I'm going to add the power. I haven't added the power. Watch what happens when I do this, is I light up all 3. Now all 3, as it turns out, are dimmer than when I did 1 by itself, because the same number of electrons are now divided between 3 different bulbs instead of just the 1. So that's a simple circuit, and we're going to play around with designing circuits and how they work and things like resistors and what all that means. Houston, we're going to do this because you guys are awesome. So as we talk about electricity, think of electrons, tiny little itty-bitty electrons moving. It's similar to this. You saw the water flowing down a river. Think of electrons as flowing down a river. The river, if you will, is the confined to like the wire. And we can measure something really important when we talk about electricity, and it's something called current. I mean, let's go back to the flowing river, right? Now, in the flowing river, we can measure how fast it moves. Typically measured in something like gallons per minute. How many gallons of water or how many liters of water are traveling per minute or per hour, something like this. We can do the same thing with current. And if you think about that, current is like speed, right? The speed of the current, or the amount of stuff moving through the wire at a time. And we're talking about stuff, we're talking about electrons, right? So we measure something in Coulomb, we measure something in current, we call it an amp, or a current. And it's measured in, if you think about it, it makes total sense, coulombs, which measures charge, which measures really the number of electrons, per unit of time per second. You could actually say the equation is Q, that's that charge. Coulomb is the symbol is Q over T is equal to A. We measure in something called an amp or an ampere, sometimes it's pronounced. So it's really a very simple equation, and once you know this, when you think of an amp, oftentimes you're going to get a problem when you say it's got so many amps. But when you think of amps, it's almost always best to break it down into its base units, which are coulombs per second. So let's take a look at this example right here. We've got the iPhone that uses a current of 2.1 amps, so A, if you will, is 2.1 amps. We've got a time. The time is 4.5 seconds, and it says how many electrons? Okay. Now remember I said if you kind of break this down, so it's not like an equation to solve, we're going to use dimensional analysis to solve this problem. So what I can say is I can say 2.1 coulombs every 1 second. See, I took that A and I wrote coulombs per second. Now notice here I've got 4.5 seconds. I can multiply that by 4.5 seconds over 1. We can flick these numbers. But I did this way because this way I get the seconds to cancel. Now I have the coulombs. But the question, right, asks how many electrons. Now we're going to pull out a number that we've seen before, right? What that number is, we know that how many coulombs there are in an electron. Remember that was given like ever ago in our units. There's 1.6 times 10 to the minus 19th coulombs for every 1 electron. So I'm going to get my calculator out, multiply 2.1 times 4.5 divided by 1.6 times 10 to the minus 19th. And that gives me 5.9 times 10 to the 19th electrons. So if you've got a current of 2.1 amps, iPhone, right, 4.5 seconds, your iPhone, This how many electrons that are traveling through your eye. I probably didn't say this earlier, but really this first video is really going to be all about kind of figuring out kind of what are the different components in what we call a circuit. So we've learned an important thing you have to measure. This is the current. The second topic is what's a battery. So a battery is something interesting. I'll just write it out here. Something that uses chemical reactions to produce electric potential, that's voltage, between its two ends. You know that when you buy a battery, it's a 9-volt battery or a whatever volt battery. And how the electrons flow, it's really a pretty tricky thing. I've taught AP chemistry, and it's a topic that we go into detail. It's pretty fascinating how batteries are made from a chemical perspective. But it's the electrons, right? We got to move the electrons through reactions, chemical reactions. Chemicals, of course, have electrons. And that's what a battery is. It's not that important that we know all the chemistry of it, but that we have a battery, and the key component of a battery is that it's voltage. It's going to provide electrical potential. Okay, and then the next term is this, a circuit. Now, circuit's interesting. All right, I'll write it all down here. So it's when charge flows through a closed path. All right, when I did that demo at the beginning, there was a closed path. The electrons had to go in a complete circuit. You've probably done circuit training, like for physical stuff, or you've run a circuit. You go from one thing next, and it's a circle. And if you break the circle, it's not a circuit anymore. And there's actually kind of like two different kinds of circuits. We call it a DC circuit. DC means direct current circuit. And what you do is, right, you have a battery. So here's a battery, right? There's actually some symbols. And then I hook a wire to it, right? And then if you put something in between, like a light bulb, it'll light the light bulb up. But you have to actually, and the light bulb, if you recall, sends wires, and it comes like that. And then that's what lights up. We can talk later about why it lights up. But it's complete circuit. If I erase this, it doesn't work. And essentially, you think about this, when you turn the switch on the light switch, turn on the lights in your house, by pulling the switch, what you're doing is you're making this like this. Actually, a switch kind of looks like this, and what you do is you close it and open it, and it turns the lights on in your house, or the power on your computer or your device, okay? Now, something is interesting about electrons. So what's happening, right, is the electrons start moving in one direction through the circuit, right? Now, there's something interesting that I think has screwed up physicists for a long time. And that is that the electrons move in one direction. That's actually what's happening. And this is a direct, so they completely make a revolution in a direct DC circuit, like a circle, a loop, right? Interestingly enough, that when physicists talk about charge, which is different than electrons, it seems like it should be the same thing. The electrons travel this way. Guess what? The charge travels this way. And you say, why did they do that? And it's actually an interesting historical note. When scientists were first learning about electricity, they didn't know that electrons existed. Electrons were discovered in like the early 1900s by a very famous experiment. Anyways, we won't get into details, but electricity was known about quite a bit before that, right? So like Ben Franklin, 17-odd, was playing around with electricity. Actually, it's his fault. He said the charge moves in this direction through a circuit, and so he got it wrong, I guess. But we've kept that same convention throughout the history of electricity, even though the electrons move in the opposite direction. I think that's weird. Another sort of fun fact to tell, and this is something I didn't know, by the way, before I was preparing for this lesson, is how fast does the electrons move through the wire? All right, so how fast? And you would think it turns on instantly. You would think they're zipping around like, yow! You know how fast they go? 1/100th of a centimeter. Is it per minute or per hour? Per second. So it's slow. They move slow. So wait a second. If I turn on the switch, right, the electron goes ee, ee, ee. I mean, this is how slow it would be. Let's say you're in your car and you turn on your lights. It's going to take the electrons 3 hours to make the circuit in your car. But your lights don't turn on 3 hours later. Why is that? It's a fascinating thing. It's because the wire, right, the wire that is, you know, the big wire thing, right, here's the wire, is filled with electrons, right? And think of them like tiny little bowling balls. Can I draw a bowling ball? Yeah. You know when you hit a bowling ball down at the bowling alley? All right, that doesn't look good. It knocks the other one down. So it's like this cascade. It's more like dominoes, maybe. The dominoes, one falls, and so the moment you start one, the electrons that are here in the wire start falling, and then they are doing work and producing energy, which is lighting up the light bulb or powering your iPhone or whatever. So they're going crazy slow, but because there's so many kind of super close, one hits another, hits another, hits another, hits another, hits another, and then the circuit is complete. So it is, for all intents and purposes, the moment you turn it on, the moment it lights up. And one last electrical term is this one, called resistance. Resistance. Now resistance is this. That because the electrons in the wire are moving around, they have collisions, and some of the collisions don't like we talked about just a couple of seconds ago, they don't like the domino effect, they keep going down, so you can actually slow the electrons down, which causes the current to go slower. I mean, think of it like I'm walking, you know, and all of a sudden I run into some quicksand. And when I run into quicksand, it's harder to run. It's like, I have to work harder. Running on sand is harder than running on concrete or something like that, because it's like friction. Think of it sort of like friction. Like friction, like if you have a wood block and you push it along the floor, that's going to make it more friction, which is going to slow everything down and not make as much work. And resistance is important. There's actually resistance inside of every electrical device. The wire has resistance, the light bulb has resistance, but we actually have things called resistors. And resistors actually slow electrons down enough so that they can do some work, okay? And we can measure resistance. So resistance, R, is measured in something called, if you think about it, it's a volt per amp. But we don't call it a volt per amp. We actually call it resistance, and we call it, here's a new term, an ohm. Ohm, right? And we use the Greek symbol omega for that. So you can say something has a 300 ohm resistor. All right? This is a really important law. It's called Ohm's law, named after Mr. Ohm, who got this out. So let's do one quick example here, right? We have a potential difference of 24 volts applied to a 150 ohm resistor. How much current do we have? So we know the voltage, right? V is 24 volts. We know R is 150 ohms. We're just going to plug this into the equation. 24 volts is equal to I times 150 ohms. Divide both sides by 150, right? And you get I, and that's the weird thing, I know, right, is 0.16 amps. Super simple to do these kinds of problems. They're going to get more complex. Houston, we don't have a problem because you're awesome. We'll see you in class.